So listen, tonight we're going to start working on proofs by cases. And the motivation, I hope, will be clear when we look at our first example of a statement. And we'll talk about, gosh, how would we prove this statement just as it stands? And I'm hoping that when you see that example, that'll motivate you to understand that sometimes we have to group mathematical objects by something that those objects have in common. And tonight, the thing that these objects, which are numbers, will have in common is a remainder when they are divided by the same divisor. We have already played dividing games, even though maybe we didn't call them dividing games. When we look at even numbers and odd numbers, we're basically saying, hey, when I divide that integer by 2, do I get a remainder of 0? In which case, of course, that number is even and looks like 2 times k, where k is an integer. Or when I divide that number by 2, do I get a remainder of 1? In which case, that integer is of the form 2k plus 1, where k is an integer, which means, of course, that it's odd. So there are 2 remainders when we're dividing by 2. You can get a remainder of 0, or you can get a remainder of 1. But of course, we're not always dividing by 2. We could divide by any non-zero divisor. So in this textbook, we're going to limit our discussion to positive divisors, although the quotient-remainder theorem, which is what we're going to look at tonight, in its full glory, deals with negative divisors as well. But we're going to look at the quotient-remainder theorem when our divisor, I just want to make sure this is in good focus, when our divisor is positive. Okay, so let's state the quotient-remainder theorem. It's also called the QR theorem. And what it's going to do is it's going to let us kind of classify integers by remainder. So let A be an integer, and B be an element of Z plus. So B is going to be our divisor for the moment. We'll change that variable to D shortly, but for right now, we're going to use B. That's standard fare. Then there exist unique integers Q and R such that A is equal to B times Q plus R, where there's a restriction on R. 0 has to be less than or equal to R, and R has to be less than B. Now, the quotient-remainder theorem actually says something that seems kind of silly. It's so obvious it seems silly. What it says is, if we have an integer A and an integer B that's positive here, then we can divide A by B and we'll get the same answer every time. That's the uniqueness claim, is that every time we divide A by B, we're going to get the same answer. We're going to get the same Q and the same R. So in this equation, A equals BQ plus R, and this inequality, double inequality about R, what do you think Q is called? Just based on the name of the theorem, what do you think the Q stands for?
Quotient?
Yep, the Q is the quotient. The Q tells us how many copies of B fit into A. And what do you think the R is then, folks?
A remainder?
Yep, it's the leftovers, it's the remainder. And of course, B is our divisor. We're dividing by B. And A, which is the quantity that's getting divided up, is called, of course, our dividend. You think of stocks and the profits from stocks being distributed to the shareholders as dividends. So A is getting divided up by the divisor B, and Q is the number of times B will fit into A, and then R is the remainder. Now, the important thing to understand about the remainder R, people, is that it cannot be negative. The remainder must be non-negative. It could be 0. For example, if we divide 15 by 5, we get a remainder of 0. Q is 3 and the remainder is 0. So it's okay for the remainder to be 0. But the remainder needs to be strictly less than the divisor b. And that makes sense because if we divide some huge number by 4 and we get a remainder that's bigger than 4 or even as large as 4, we go back in there and we pull out as many more copies of 4 as we can because we don't want the remainder to be as large as the divisor. If our remainder's bigger than or even as big as our divisor, it means Q's not big enough. We need to go back and make Q bigger. So let's look at some examples. Our example 1 tonight, we're going to suppose A and B, we're going to look at several examples, are given as below. And we want to find the Q and the R, find Q and R guaranteed by the QR theorem. Everybody just calls it the QR theorem once we know what that stands for. All right. And so here's our equation. Here's our information about R. All right. Roman numeral little 1. Let's say A is 99 and B is 2. I'm just going to go ahead and list our examples and then we'll do our work here on the side. 2, A is 37 and B is 5. 3, A is negative 37 and B is 5. 4, A is 9 and B is 12. And then finally 5, A is 120 and B is 10. So we're going to use the QR theorem for each one of these, and we're going to find the Q and the R. So we can do the work right here. Okay, so let's do the first one. A is 99. So we write 99 equals, because of course we've got our equation up here. B is 2, so 2 times some quotient plus some remainder. And then we can just, write our quotient and our remainder as answers over here. So what is the quotient? How many times can we fit 2 into 99? Not quite 50, right?
Is it 49 times?
It is. Nice. Nice job, Ronnie. 49. So 49 times 2 is 98. So what is our remainder here? I'm going to open the chat so I can see.
1.
Good. 1. Nicely done. Somebody's chatting in 1. Okay, great. That's you, Ronnie. Okay, great. So our Q is 49 and our R is 1. Any questions on that? All right, let's do the next one. 37 is 5 times some Q plus an R. So how many times does 5 fit into 37, folks? I know, right? It's been a while since we've done our multiplication tables.
7.
See, 7 times 5 is certainly right. That's 35. And so what's our remainder then?
2.
Yep. Okay, so this looks, fairly straightforward, and it is. Q is 7, R is 2. It gets a little interesting when our dividend is a negative number, because we are not allowed to have a negative remainder. Remember, our remainder has to be no smaller than 0, and it cannot be as large as the divisor b. So when it's negative 37, what we're doing on the number line here, here's negative 37. Here's 0. We're jumping by jumps of size 5, but we're jumping backwards. And we have to actually overshoot the negative value so that we can come back to the right with a non-negative remainder. So what should we multiply 5 by? Since
Negative
5,
8.
yeah, negative 8, because that takes us down to negative 40, and then we can come back with a positive remainder of 3. Everybody see that? So this time, of course, we get a negative quotient because our dividend was negative and our divisor was positive. All right, so that's one of the kind of tricky things that can happen is if your dividend is negative. In 4, this is another kind of interesting thing. We're trying to divide 9 by 12. Well, how many times does 12 fit into 9?
0.
0, exactly. The quotient is actually 0. When the divisor is larger than the dividend, then the quotient will be 0, and the remainder will be the dividend. Questions? And finally, this last one is super simple because I wanted to show you an example where the divisor fits into the dividend evenly. In other words, the remainder is 0, of course. 120, of course, is 10 times 12 plus no leftovers, right? So the remainder is 0. And that happens when the divisor divides into the dividend. You know, that's the definition of divides. Okay, so let's just kind of think about this idea of a divisor. Here's a fact. We think about kind of the simplest divisor that's not trivial. 1 is a trivial divisor, right? Everything is divisible by 1. But when the divisor D, I'm going to change the name now. We're going to call it D, is equal to 2. Think about the possible remainders. And I did mention this at the beginning of class. If the divisor, which now we're calling D, is actually 2, that means the remainder has to satisfy 0 is less than or equal to the remainder is less than 2. So what are the possible remainders?
0 and 1.
Exactly. There are only 2 possible remainders. And, you know, that makes sense when we think about what happens when we look at integers and we ask, is that integer divisible by 2? If it is, it's an even integer. If it's not, it's an odd integer. So what happens to the set of integers when we are dividing by d equals 2 is the integers get split up into 2 subsets. And one of these subsets we call 2z, that's the evens. And the other subset we call 2z plus 1. Of course, that's the odds. And the evens are all of the integers that yield a remainder of 0 when they're divided by 2, and the odds, of course, yield a remainder of 1. Now, this is new notation, the idea of taking a whole set like Z and multiplying it by a number, or taking a whole set like 2Z and adding a number to it. But this is a mathematically valid operation, and I want to show you why. So let's take a closer look at the evens and odds, and let's make sense out of this notation, 2Z and 2Z plus 1. So let's take a closer look at the evens and the odds. Now we know that Z is a set that we could write using roster notation or list notation, right? With our ellipses, our dots, okay? So we recognize that this set is what we call the integers, right? 2Z, the evens, is what we get when we take this entire set and we multiply it by 2. But what does it mean when I say multiply a set by 2? What it means is you take each element of the set and you multiply each element one by 2. So we'll just leave our dots. But of course, what happens when we multiply -3 by 2? What do we get?
-6.
Sure. And when we multiply -2 by 2, we get -4. When we multiply -1 by 2, we get -2. When we multiply 0 by 2, well, that's still 0. And then 1 times 2 is 2, and 2 times 2 is 4, and 3 times 2 is, see what I mean? This is what we recognize to be the set of even numbers. So this notation actually makes good sense. And in the same spirit, it is okay to take a set and shift the whole set to the right by 1. That's what's happening when we take 2Z and we add 1. What we're actually doing is we're saying, okay, each set of 2Z, each element of 2Z is going to have a +1 added to it. So let's take a look and see what happens. When we add 1 to -6, what do we get, folks?
-5.
That's right. And what happens when we take -4 plus 1?
-3.
Good. Keep going. -2 plus 1.
-1.
0 plus 1.
1.
And good. 2 plus 1.
3.
4 plus 1.
5.
Yes. And, I mean, we could go ahead and put 7, but I think we see enough to see the point. These are the odds. You see what I mean? So this notation actually does make sense. So from now on, 2Z is another name for the evens, and 2Z plus 1 is another name for the odds. Now, let's just up the ante a little bit, okay? We just played dividing by 2 games, but the divisor could be something else. So let's look at what happens when the divisor D is 3. Well, when the divisor D is 3, we get these possible remainders. Now remember, our remainder cannot be negative. It can be 0, but our remainder cannot be as large as the divisor. So R could be 0, right? But what other remainders could we get if we're dividing by 3? Anybody?
1 and 2?
Yep. So the cool thing is, folks, if you're starting to see a kind of a pattern here, when the divisor is 3, there are 3 possible remainders, 0, 1, 2. If the divisor was 4, there'd be 4 possible remainders, 0, 1, 2, and 3. You see what I'm saying? And we can play this game of thinking about how the integers get partitioned, that's a thing, split up, into 3 subsets based on the remainder upon division by 3. So there's a set called 3z. These are the actual multiples of 3, like 0, 3, 6, 9, -3, -6. These are the elements of the integers that yield a remainder of 0 when they're divided by 3. Then there's 3z plus 1. These are the elements of the integers, z, that yield a remainder of 1 when they're divided by 3. And then, of course, what do you think this other subset is called?
Three Z plus 2.
Exactly. Nice job. 3z plus 2. Of course, that's the set of integers that give the remainder of 2. Now, you might say, well, why are we even bothering to do this? This seems silly. Well, it turns out, folks, remainders are very, very important. The entire RSA encryption code is based on the idea of having very, very, very large divisors, so big that it's hard to find their prime factors, and then looking at remainders when numbers are divided by these very large divisors. It's a thing. I mean, it's an important thing. And if you decide to take cryptography at Towson, and I encourage you to do that, you will see exactly how important remainders are in the theory of computing. But for now, let's just see if we can get our heads around these sets, all right? So here we're looking at dividing by 3. And for example, just to get you started, here in this set 3z, well, by the way, the remainder that is being represented by the set is always an element of the set. So I claim 0 is in 3z. And it is. We can check it. 0 is, right? It's A equals dq plus r, right? So, well, 0 is equal to d is 3 times 0 plus, well, the remainder, of course, is 0. So it really does yield a remainder of 0 when it's divided by 3. Another number that's in 3z would be, say, 6. 6 is 3 times 2 plus this same remainder, 0. Now, I've made a claim. Let me back it up. I've claimed that the remainder is always in the class that's named with that remainder. So in other words, my claim is 1 is going to be in the class 3z plus 1. Let's see. Well, 1 is equal to 3 times something plus 1. What is the quotient here? That's right, 0.
2.
Nicely done. I claim -2 is in 3z plus 1. Can you write the equation that verifies that -2 actually yields a remainder of 1 when you divide it by 3? What would the quotient need to be?
-1.
Exactly. Nicely done. All right. And up here in 3z plus 2, I'd like to start with 2. Do a couple more. How about -7? I claim -7 is in 3z plus 2. Can you verify it? What would the quotient be?
-3.
Correct. We have to overshoot. We have to go past -7 down to -9 so we can come back with this positive remainder 2. And -4 is 3 times -2 plus 2. Okay, I think that's good. I don't want to just beat this horse until it's dead. But I do want to show you a picture of what happens when we look at the integers just as a set on the line, and when we think about grouping them together by remainder. So rather than take the time to draw this, it's already posted in the notes, but let me just show you what's going on here. If we denote with a red square the integers that leave a remainder of 0, and a blue triangle those that leave a remainder of 1, and a green circle the integers that leave a remainder of 2 when they're divided by d equals 3, look what happens to the number line. Do you see it's like every third integer is going to have the same remainder as the other ones. You can just jump by jumps of size 3. See how all the green ones are 3 apart? And the difference between any of the integers that are in the same group together is always divisible by 3. Like look at -3 and 9, okay? They're both in the red group. R is 0, right? They yield a remainder of 0 when you divide them by 3. Well, the difference between -3 and 9 is 12. I mean, it's -12 if you think about it one way, but it's 12 in magnitude. 12 is a multiple of 3. If you take any two of the elements in the R equals 1 class, like -8 and 4, well, the difference between those is 12. So let's say -8 and 7. The difference between -8 and 7 is 15, but that's divisible by 3, you see. So this is kind of what it does to the number line. And you can think about, okay, if that's the way it works when D is 3, it'll work in a similar way if D is 4, except there would be every fourth one would be in the same group with the ones before, you see. Questions? So let's look at the most general case. We split up Z first with D equals 2 into the evens and odds, and now we've split Z up into 3 subsets, based on D equals 3. What happens for the general divisor D? So let's think about the divisor, just any D greater than 1. We're not going to, 1 isn't very interesting. There is no remainder. Every integer is in its own class by itself. It's like an infinite little bunch of singleton sets, okay? What are the possible remainders, though, in general, if we're dividing by D? All right, well, I'll start you off. We'll assume, D is bigger than 1. So at least we have 0. And then if D's, at least as big as 2, so 1 is a possible remainder. Keep on going. What is the biggest remainder possible? What is the largest remainder that would be legal according to the QR theorem?
The number itself.
When we divide by 3, are we allowed to get a remainder of 3?
No.
We need a remainder of 2 is the biggest. If we're dividing by 5, what would be the biggest remainder that we would be able to have, folks?
4.
So if we're dividing by D, what's the largest remainder that we're allowed to have?
D minus 1.
That's it, D minus 1. And, you can think about the integers as being, a big pizza. And each slice would be one of the remainders, like dz, all the multiples of d. That's when the remainder is 0. dz plus 1. These would be the integers that yield a remainder of 1 when they're divided by d. All the way up to, I didn't mean to make this look like it's exactly half, because it's not really like that. But dz plus the biggest remainder, which is d minus 1, would be the last slice in this pie. And there are always d classes. And there's an error in the notes that are posted. It's a total of D classes, not D minus 1. 0, 1, 2, up to D minus 1. Because we have the 0, it's a total of D classes. So I'll correct the notes of integers grouped by remainder. Yeah, that's a bad little typo that I put in there. It's D classes, not D minus 1. All right, so like I said, mathematicians care about remainders. They matter. It's a big deal. So here are a couple of little functions that you've probably seen, folks. They're called A mod D and A div D. Have you ever seen these in any computing language that you've played with? Or let's define them, okay? Have you? Have you seen them? Yeah. Infinity minus 1. I like that. Yeah, really. Honestly, considering that the divisor could be, any huge number, I see why you would say that the biggest remainder is infinity minus 1. But we think about it within the bounds of a particular divisor. Ronnie had put that the biggest remainder would be infinity minus 1 because he's thinking about, hey, these divisors could be, infinitely large. And in a sense, that's true, right? But we think about this question with regards to a specific finite D, Ronnie, okay? That's an interesting comment there. So here's our definition for A mod D and A div D, and it's completely based on the QR theorem, okay? So given integer A and positive divisor D, here are our definitions. 1, A mod D is the R, the remainder, guaranteed by the QR theorem. And A div D is the quotient Q that's guaranteed by the QR theorem. I'll write the QR theorem down one more time here so we have it right in front of us. It's where A is equal to D times Q plus R. 0 is less than or equal to R is strictly less than D, okay? Now, let's look at an example where we just practice finding A mod D and A div D. And this will mirror what you're going to see on your homework in WebAssign, which of course is already up and is due Friday as usual. And your next special homework is due next Monday. There'll be a couple of problems on your special homework that we'll need to talk about as late as Wednesday. But I wanted to go ahead and get those up. Okay, so we'll do 1. Oh, I need instructions, my bad. Find A mod D and A div D. So A mod D is the remainder, and A div D is going to be the quotient for, okay, here we go. 1, A is equal to 49, D is equal to 3. 2, A is equal to negative 150, and D is equal to 4, and 3. Let's let A equal 60 and D equals 7. So we'll do some work over here, and then we can write our answers here. The bottom line is you just have to go ahead and use this equation, of course, where A is DQ plus R, making sure that the remainder is in the correct boundaries. So 49 is equal to 3 times something plus something. Negative 150 is going to equal 4 times something plus something. And 60 will equal 7 times something plus something. All right. So let's find these values. What's the quotient for this first one where A is 49 and D is 3?
16.
That's right, because 16 times 3 is 48. And what's our remainder then? 1, of course, to get 49. Good. So our solution of 49 mod 3 is, okay, mod is the remainder, so that's 1. And 49 div 3 is the quotient, that's 16. So take a few minutes and do these other two. Okay, so for number 2, what is the quotient?
38.
Almost. We need a sign adjustment.
Negative 38.
That's right. We gotta. And if you're wondering, how we get that, you could think about it this way. We're dividing 150 by 4, sort of. Half of 150, like half of $1.50 is 75 cents. And half of that is 37.5 cents. But we know we have to overshoot. So you try negative 38. And yeah, that'll take you backwards. And then what do we have to come back with? I think this becomes negative 152. So what's our remainder, folks?
2.
Yep, we got to come back with the positive remainder. So negative 150 mod 4, mod is the remainder, that's the 2. And negative 150 div 4 is negative 38. All right, let's do the last one. What's the quotient when we're dividing 60 by 7, everybody?
8.
8, yeah. You got to know your times tables, folks. And then our remainder would be, what, 4? It's 4, right? 56 plus 4, 60, yep. So 60 mod 7 is 4, and 60 div 7 is 8. Okay, just a little practice there. But there are even, these are kind of trivial games, but that's fine. These are real functions that you may actually see in your programming, future somewhere down the line. But the real important games are based on remainder. So let's take a look at some important things that we need to understand about what happens when we play remainder games. Okay. So games based on remainder. We're going to learn some important facts in the process of learning the rules of these games. So let's just suppose, for example, 3. Suppose A and B are integers. And A mod 6 is equal to 2, and B mod 6 is equal to 3. Notice we don't even know what A and B are here, okay? We just know that they yield these remainders when they're divided by 6. 1, we're going to try to find A plus B mod 6. And 2, we're going to find A times B, or AB mod 6. All right? Now, in order to play the game, listen, we know that proof money involves equations, always. We need equations. So we need a helpful translation from mod to an equation. And if we're really lucky, this translation will actually go both ways, and it does. All right, remember, if we're dividing by a divisor D, A mod D is equal to the remainder, and we know that 0 is less than or equal to R is strictly less than D. But folks, that means that A equals DQ plus R, where Q is some integer that we call the quotient. We don't even really care what Q is at this stage. All we really care about is the fact that it's an integer. Well, it turns out this goes both ways. I mean, this is a direct translation from a statement about A mod D equaling R and an equation involving A. And that is proof money. And this is going to be exactly what we're going to use so that we'll be able to do some substitution. We always use our equations for substitution, right? When we're writing proofs about evens and odds, we wind up substituting in, x equals 2k or x equals 2k plus 1. We also need some facts. We need some helpful facts to help us understand what A plus B mod 6 actually means. Well, A plus B mod D for any divisor D is equal to A mod D plus B mod D. This is true for any divisor D. And AB mod D is equal to A mod D times B mod D. And I can prove this, and I'll be happy to prove this during office hours sometime. I'm going to suppress the proof right now unless we have time at the end of lecture, in which case I'll prove these. These facts arise directly from this translation back and forth between the equations that we understand as the defining equations for what it means to talk about A mod D. Okay, so now we are ready to attack example 3 and look for a solution. So first, we're going to translate in the direction left to right, okay, of this double arrow. All right, what am I talking about? I'm talking about, we know that A mod 6 equals 2. Okay, so we know that A mod 6 is equal to 2. So we translate, and that means, hey, A is equal to 6 times Q plus 2. In fact, I'm going to call it Q1 because we're going to have another one in a minute from B, another equation, okay? Because we're given that A mod 6 equals 2. So this translation gives us an equation. And B mod 6 equals 3 translates to an equation. That B is equal to 6 times some quotient, we'll say Q sub 2 plus 3, because the remainder is 3. Oops, it's supposed to be Q2. And now we're going to try to find, we've got our proof money, you see. We've got this information about A and about Q1. We've got this information about B, and we know Q2 is an integer, right? So we're going to use all this now and find A plus B mod 6. Well, A plus B mod D is A mod D plus B mod D. So A plus B mod 6 is A mod 6 plus B mod 6. And we know now what A mod 6 is. A mod 6 means that A is equal to 6Q plus 1. So sorry, I'm just going to write 6Q1, 6Q1 plus 2, my bad. And B, so we're really looking at A plus B here. So A plus B is A, which is 6Q1 plus 2, plus B, which is 6Q2 plus 3. Sorry for the index. Well, what is that? And look what we're trying to find. We're trying to find A plus B mod 6. We're looking for the left side of the translation relationship. Well, if we can get a 6 factored out, because our divisor D is 6, with an integer plus a legal remainder, mod 6, we'll be good to go. Well, check this out. This is 6Q1 plus 6Q2. I'll just get those gathered together close. And then, of course, plus 2 plus 3 is plus 5. And plus 5 is a legal remainder. It's legal if you're dividing by 6. So it's 6 times Q1 plus Q2 quantity plus 5. So you see, so this Q1 plus Q2, this is our Q. So A plus B equals 6 times an integer plus 5. And now we simply translate in this direction. We have the equation 6Q plus R, where R is a remainder that's appropriate for dividing by 6. And so that means that A plus B mod 6 is equal, in fact, to 5. So we translate back in this other direction. Questions? All right, let's see if we can solve AB mod 6, okay? This was part 1, A plus B mod 6. Now let's work on finding AB mod 6. Let's keep our equations where we can see them. This information about A and B. Okay. So AB mod 6 is going to equal A mod 6 times B mod 6. So what is AB? Well, A is 6Q1 plus 2, and B is 6Q2 plus 3. So AB is 36Q1Q2 plus what? 18Q1 plus 12Q2 plus 2 times 3 is plus 6. Now we're dividing by 6. So to use our translation equation, this translation relation, put it where we can see it, to go back this way with D equals 6, we realize we've got to pull a 6 out of as much as we can. We'll check out the leftover here. Is 6 a legal remainder if the divisor is 6? Can we have a remainder of 6?
No.
No, it's too big, right? So in fact, we can pull a 6 out of all of this. And we have this huge Q. It's 6 times the quantity, of course, when we pull 6 out of 36 Q1, Q2, we've got 6 Q1, Q2 left over, plus 3 Q1, plus 2 Q2, plus 1. And look, it's plus nothing. 0 is left over there. And this big expression is our Q, which is an integer. So now we're ready to translate from this equation, 6 times a big Q plus 0, back to finding AB mod 6. What is it? What's the
Is it
left
zero?
here? Go ahead.
0.
Yeah, it's the 0. There was nothing left over. So when we translate back, 6 is so big that we have to pull 6 out of it, and there's nothing left over. So when we translate it back. Now, I want to show you one more. Let's do one more. We're going to use the same A and B, but I'm going to add in a C. Okay, so this is going to be example 3, part 3. Okay, so let's just suppose that we have what we had. A mod 6 is 2. B mod 6 is 3. But now let's say that we have C mod 6 is 4. Okay? Let's find the quantity A plus B plus C mod 6. Okay? So just recall, we have the equations for A and B. Here's what they were. A is equal to 6Q1 plus 3. Q1 is in Z because A mod 6 was equal to 2. B was equal to 6Q2 plus 2. Wait a minute. Do I have this backwards? Ooh, I've got it backwards. A mod 6 was 2, not 3. My bad. This is 6Q1 plus 2. B mod 6 is 3. So B equals 6Q2 plus 3. Q2 is an element of Z. Can you write an equation for C now?
6Q3 plus 4.
That's right. 6Q3 plus 4. Very good. Where Q3 is in Z. So now we've got everything that we need, you know. So we had this, and we had this. So now we've also got this. So now let's crank it out. A plus B plus C mod 6. It's going to equal A mod 6 plus B mod 6 plus C mod 6. Now, actually, folks, you can actually realize that A mod 6, is 2. Like once you realize this, you can just say, hey, this is going to be 2 plus 3 plus 4. But I want to just show you what A plus B plus C really looks like. I wanted to show you why it works that way. A plus B plus C looks like this. But of course, we're going to pull a 6 out of, well, hang on. Let's see what we've got. We've got 6Q1 plus 6Q2 plus 6Q3 plus what, 9? All right. We've got 9. And that's why I wanted to do this one, because 9 is not a legal remainder when we're dividing by 6. It's too big. So what do you do when it's not actually a multiple of 6 so that, it all goes away to 0? Is you apply the QR theorem to the remainder, and we realize, oh, 9 can be divided by 6, and it's equal to 6 plus a remainder of 3. And then you can pull the 6 out of the first 4 terms. So we have 6 times Q1 plus Q2 plus Q3 plus 1. And then this plus 3 is now left out. And it is an appropriate size to be a remainder, mod 6. So we translate back now. So A plus B plus C mod 6 is 3. Let me get my arrow out of my own way. Questions? Okay. So the whole motivation for really examining quotients and remainders is more about the remainders and understanding that when we divide by a given divisor, it really does split the integers up into classes based on remainder. And it is those classes that will help us figure out cases to write proofs that we would not be able to write if we did not use cases. So now, that's all fun and games. We enjoy, working with quotients and remainders and playing those games. But the real application is to be able to write a proof by cases. And in case you're wondering, we are still in section 4.5. So here's the question. This is supposed to be the motivating question. Suppose you are asked to prove this. For all n in z, so for all n that are integers, n squared plus 3n plus 5 is odd. So let's say you're asked to prove that. All right, let's just go ahead and execute good step 1, and let's write it as an if-then. It's if n is in z, then n squared plus 3n plus 5 is odd. Okay, so that's the statement. And we're well aware that this statement has a hypothesis. It's a real simple hypothesis. It's just that n is an integer. The hypothesis in our proofs by cases will always be that n is an integer. And here's the desired conclusion. We want to prove that that expression represents an odd number. How are we going to do that? Do you see the problem inherent in this? To prove that this expression is odd, we have to get it looking like an odd number. In other words, we have to get it looking like 2 times an integer plus 1. But there's no 2 in there at all. So the answer is, hey, let's use proof by cases, because when we do that, thinking about dividing by 2, we will be able to introduce some 2's into the mix, and then we'll be able to get what we want. So we're going to use cases based on the divisor that's in play. The divisor that's in play. Well, when we're talking about something being even or odd, the divisor in play is 2, because that's naturally what's going on. If we're talking about the parity of an integer, its evenness or oddness, we're talking about divide it by 2 and see if you get a remainder of 1 or a remainder of 0. In this case, we're shooting for a remainder of 1. So there are 2 steps to this process. The first step is to figure out what the divisor is. So look at the desired conclusion. So, you look at your then part, the desired conclusion, right? You will find information there about the divisor in play. Call it D. All right. So once we figure out what the divisor is, that's step 1. Now, step 2, we got to figure out how to implement the cases. For step 2, you look at the object in the hypothesis. It's always going to be an integer. So for step 2, look at the object. In this case, it's n, in the hypothesis. Set up D cases using the quotient-remainder theorem. I'll show you how, obviously. With the object in the hypothesis being the dividend A. With the object in the hypothesis being the object A, the dividend. So what we're going to use is the fact that A is known to equal D times Q plus R, where 0 is less than or equal to R is less than D. But the point is, depending upon how big D is, it'll give us D cases. Let me show you what I mean. Once you see it once, it's going to make sense, I hope. So we're going to call this example 4. So let's prove the following. If n is in Z, then n squared plus 3n plus 5 is odd, okay? All right, so let's do step 1. We look at the conclusion, and you will find information about the divisor. When the conclusion says you want to prove something is even or odd, that tells you the divisor D is 2. It's 2 because we want to show something is odd. Step 2, we're going to apply D cases to the object in the hypothesis. So the object in the hypothesis is this integer n. So what we say is by the QR theorem with D equals 2, we know either n is equal to 2 times q or n is equal to 2 times q plus 1, where q is an integer. These are the two possible cases because the two possible remainders when d is 2 are a remainder of plus 0, which we don't even write, or a remainder of 1, which is written here. Basically, if you're trying to prove something is even or odd, you break up your cases applied to your integer n from the hypothesis. It's either even or odd. Okay, so now let me show you how to start writing this up. And this is actually kind of the wording that we will use in the proof. All right, I'm going to keep this where we can see it. This is our first proof by cases. All right, so it's example 4, proof. I don't need to rewrite the statement because it's right in front of us here, right here. So assume n is in Z. Just as usual, we assume the hypothesis because we are still using direct proof. Even though it's proof by cases, each case is going to be done using direct proof. Now let's go ahead and write our wish. We want to keep with our good habits. We wish to show that n squared plus 3n plus 5 is odd. Now this is the deal. Just imagine that you want to get from Baltimore to Chicago. Okay, maybe you're going to go to the Science Institute in Chicago or the Museum of Science and Industry. It's amazing. If you've never been there, it's amazing. One way to go would be to go through, I don't know, Detroit. Another way would be to fly through, let's say, Minneapolis. No matter which way you go, you want to end up in Chicago. It's the same way with proof by cases, folks. One way we're going to go where we assume n is even and looks like 2q. In the other case, the way we're going to go is we're going to assume n equals 2q plus 1. But in both of those cases, we want to end up at the same place and we want to show the same wish in both cases. Okay? Now here's how we set it up before we actually start the cases. Using the QR theorem, that's the kind of wording you want to tell your reader what you're doing. With D equals 2, it's polite to tell your reader what divisor you're dealing with. We have 2 cases. We always have D cases, whatever D is. If D was 3, we'd have 3 cases. And they are that either n is equal to 2q or n is equal to 2q plus 1. And for both of those, q is in Z. Okay? By the way, we always use the inclusive or, but because the quotient-remainder theorem tells us that when we divide n by 2, we get a unique remainder, that uniqueness clause actually makes this an XOR. It's not going to affect the way that we do the proof, but I thought you might find that interesting. That, see, we don't know what n is. N might be 100. N might be 101. We don't know. All we know is whatever n is, we're guaranteed that when we divide it by 2, we'll get the same remainder every time we divide that particular integer by 2. So we also know that you can't get, two different remainders. Well, because you get the same one every time. Okay, so I'm going to go ahead and skip a line because that's really nice for formatting case 1. Let's suppose n equals 2q, where q is in Z. I'm going to rewrite the wish. I know it seems redundant, but at this stage of the game, some students don't understand that it's the same wish in every case. All right, here we go. We're going to look at n squared plus 3n plus 5. We have an equation for n. It's equal to 2q, right? Here we go. So let's just do it. N squared plus 3n plus 5 is equal to 2q quantity squared plus 3 times 2q plus 5. Now let's just remember what we're shooting for. We're trying to show that this thing is odd. So what does this look like? This is 4q squared plus 6q, and 5 we can write as 4 plus 1. In other words, 2 times 2 plus 1. And that will help us. And now we can factor a 2 out of 4q squared, leaving 2q squared, and out of 6q, leaving 3q, and out of 4, of course, leaving 2. And then we've got a plus 1 left over. And yay, all we got to do is talk about why this expression inside the parentheses is an integer. So we invoke closure. So since q is in Z, and Z is closed under what? Products, a multiplication and addition. Multiplication and addition. We see that, and I'll call it M equals 2q squared plus 3q plus 2 is in fact NZ. So n squared plus 3n plus 5 equals 2m plus 1, where m is in Z, which makes it odd. By definition of odd. All right, now we're halfway home and we're at time, but this is okay because I planned to ask you to write case 2. You bring it to class Wednesday and we're going to go over this. Please go ahead and write it up because we want to compare. But of course, this is the case where n equals 2q plus 1, right? We have these two cases, right? So that would be what you would suppose. I'll just start you off. Suppose n equals 2q plus 1. I don't need parentheses around it yet, but you will want parentheses around it when you substitute it in, where q is in Z. And just to emphasize, it's the same wish. We wish to show n squared plus 3n plus 5 is odd. Okay, so you can work through the algebra of that and finish that. Once you've done both cases, the proof is done. Questions? So again, if you need to see me, whatever you need from me to help you get your homework done, reach out if there is anything that I can do. I know that some of you have incredibly busy schedules and challenging, piles of work in front of you, but if you're in this class and you plan to stay, you want to push through the homework, okay? I have uploaded your graded homework number 5. I waited until actually this morning, hoping, as many people as possible would go ahead and upload something. So thank you to those of you who did that. And the next homework is due on Monday, because the following Monday, 2 weeks from today, we have our second test, and it is on proof writing. So I need to get that homework from you so that I can give you some feedback next week. What's the lay of the land? We're going to do another proof by cases on Wednesday, and and review the end of this proof by cases. Then we're going to learn different proof methods, because direct proof, where we assume P and wish to prove Q, is not the only way to prove if P then Q. So we'll learn proof by contraposition, and we'll start proof by contradiction on Wednesday and finish that up on Monday. Your special homework number 7 won't have any proof by contradiction on it. There'll be a little mini homework later next week for you to work on to get practice with that. But it does have a proof by contrapositive, which we will learn on Wednesday. So I hope everybody has a good night. I'll hang out for a little while. Any questions? Okay, I'm a little bit over time. I apologize for that. I'll stop recording.